Now if we try to use partial derivatives to see how this function behaves near its critical points, the x derivative is y, the y derivative is x. The second x derivative is 0. And the second y derivative is 0. Meaning that in the xz plane, the coordinate plane, the xz, the specific xz, this is an xz type plane where y equals cx, so it's not the xz coordinate plane. And maybe that's a little confusing the way I drew it. In any case, in the xz coordinate plane, the graph would be a straight line. In the yz coordinate plane, the graph will be a straight line. And actually in both of those planes, I'd have to draw it to make sense of what I'm about to say, so I'm not going to say it. Okay. The fxy derivative, which is the partial with respect to y, the partial with respect to x, is equal, not to 0 though, to 1. Also, fyx is equal to 1. To test for the kind of behavior we have and to distinguish the behavior of this function, the saddle point behavior, from that of, say, a paraboloid, where where you do have an absolute minimum or an absolute maximum at the origin, we use a test that involves not just the second x and the second y derivatives, which gives you concavity in the x and the y direction. We find that we have 0 concavity in the x and the y direction. We also look at the xy and the yx derivatives, which are of course equal. And we put those together with the second x partial derivative, second y partial derivative, and we get a test. There are reasons for the test, but the test is actually very easy to apply. And the test just says that you calculate this d thing, kind of like a discriminant, but it's not a discriminant, kind of a generalized discriminant. We do the second x partial times the second y partial and subtract the mixed partials, the xy partial and the yx partial. Of course, the xy partial and the yx partial are equal, so that's equivalent to just subtracting the xy partial squared, or the yx partial squared. It would be the same. Okay, this is our test for whether we have a maximum, a minimum, or a critical point. Okay, and it works unless this whole thing turns out to be 0. If this turns out to be 0, we don't know what we've got. We've got to use some other means of figuring out what the graph looks like. But let's think about what this means. Okay, if the x and y partials are both positive, that means the graph is concave up if you slice it in the x direction, concave up if you slice it in the y direction. Well, that would seem to end the discussion. If you slice it in the x direction, it's opening upward. If you slice it in the y direction, it's opening upward. But it doesn't necessarily tell you that it's opening upward if you slice it at 45 degrees to the axis. Okay, now, if it's opening upward, if both of these are if both of these have the same sign, then either they're both opening upward, which would tend to indicate a minimum point at your critical point, or if they're both negative, that would mean they're both opening in both directions. The graph opens down away from your critical point. The product of these would be positive either way, as long as these two have the same sign. Now, if these two have the opposite signs, that means it opens up in one direction, down in the other, and you're done for. You know, if it opens up in one direction and down in the other, that you're not going to have a relative maximum or a relative minimum. So if this product is negative, which indicates that these have different signs, this quantity is going to be negative. Okay? because this quantity is always going to be, when you subtract this quantity, you're always going to get a negative from this because you're squaring something. That square has to be positive, so when you subtract, you're going to get a negative. If you've already negative, it's going to go more negative. Okay, so the fact that you have this doesn't change the fact that if these two signs are different, you're going to get a negative result. Okay, and the negative result is going to indicate that you have a saddle point. Okay, now there's another possibility, which is both of these have the same sign, but the square of the xy derivative is big enough to mess things up. Okay, so if the square of the xy derivative is big enough, this can overcome the positive of this. And the test is that if this thing is negative, you have a saddle point. If it's positive, you have either a max or a min. If it's zero, you don't know what you have. Applying that to this function, we see that the xx derivative is 0, the yy derivative is 0, so we've got 0 here. The fxy is 1, so we have fxy squared is 1, we have negative 1. That indicates the saddle point. Now there are reasons why this works. We don't want to talk about it just yet. The whole idea is you find your critical point by setting the x derivative equal to 0 and the y derivative equal to 0. You then test the critical point with this test to see whether you have a maximum, a minimum, according to the signs of the fxx and fyy, or a saddle point if the fxy is too big. We're going to apply that to an example in the next video.